we were in the process of proving the constancy theorem. So let's see how that works out. So T in D and U, it's an N current. And here U is open in Rn. So notice this, N equals P equals N in this case. Same N. And boundary of T equals 0. Then, oh yeah, usual problem, U connected, open connected. In Rn. So again, let me emphasize, we're talking about T is a top dimensional current then, right? Top dimension. P equals N. Normally we'd have an N current in Rp where P was bigger than N, but in this case it's P equals N. Then then there exists a constant C. With T equals C times U. Okay, so we'd done the main step in the proof. We actually proved that T of A sigma dx1 wedge dxn is actually representable in terms of an integral of A times a function times a bounded function theta n. And this is for every, this is integral over Rn, and this is for every A. We actually proved this for every A in L1, but now we only care about A in C infinity C of the ball of radius rho centered at x0. Remember, the picture was this. We had U here, the open set, and we took an arbitrary ball, x0, centered at x0, radius rho, in that ball. And then we proved this, where theta sigma is bounded. Now, one thing we have to watch out for is here, there's no guarantee a priori that theta sigma is bounded independent of sigma. It's just bounded. We've got to check that it's bounded independent of sigma. And but we don't know that yet. So so now we haven't yet used the fact that boundary of T is 0. So consider consider the following n-1 form. A sigma times dx1 wedge, etc., leaving out dxj. So it's dxj minus 1, dxj plus 1, up to dxn. So notice dxj is missing here. So this is an n-1 form. And let's compute a d of this. So call this omega. And d of omega is equal to d a sigma wedge with this. And of course that's, that's right. And that's sum I equals 1 up to n di a sigma dxi wedge the remaining guys, dx1, dxj minus 1, dxj plus 1, up to dxn, like that. And now notice that this is 0 unless I is equal to j, because there will be a repetition here if I is not equal to j, right? So this is 0 unless I is equal to j. If I is equal to j, you can put it in there and put in a factor minus 1 to the j. So this is minus 1, or rather minus 1 to the j minus 1. So it's minus 1 to the j minus 1, sum of dj a sigma. All the other terms are 0. You just get the jth partial of dx1 wedge up to dxn. Of course, now that's d of an n minus 1 form, so as you expect, that's in dn now. Okay, so that's what you get. So now notice a sigma is the mollified version of sigma. So remember what that looks like. That's the integral of the mollifying function, x minus y, a sigma at x, is phi sigma x minus y, a y dy. That's what that looks like. Remember we talked about mollifying last time. And notice that dj of a sigma x, well, that's the same as dj of this. You can put the derivative under the integral sign, of course. It's partial with respect to the jth x coordinate of phi sigma x minus y, ay dy. And by the chain rule, by a trivial case of the chain rule, I can replace the partial with respect to xj by the partial with respect to yj, as long as I change the sign, minus 1. So this is minus partial with respect to the yj variable of the same thing, phi sigma x minus y, ay dy. And now I can just integrate by parts. Remember, this has got compact support, and this has too. So you can integrate by parts. And this is, minus becomes plus. So this is phi sigma x minus y dja at y dy. So the upshot of all that is that dj of a sigma is the same as dj of a sigma. In other words, mollification and taking partial derivatives commute. You can either take the partial derivative first and then mollify, or you can mollify, then take the partial derivative. Either way, you get the same answer. So this is dj of a sigma. But then this applies. So this means that T of d omega, which is that, is exactly this, but with dja in place of a. So this is equal to the integral Rn dja phi sigma dln. So that's that. Now on the other hand, notice this is 0, because this is, by definition of boundary, this is that. And that's 0 by assumption. We're assuming that boundary T is 0. So that means this is 0. This equals 0 for every j equals 1 up to n, and for every a in C infinity with compact support on B sigma x0. Now, I think you can see, you can actually prove it for yourself, but I think you can see, obviously, this means that phi sigma has to be a constant, right? In the language of distributions, this says the distribution derivatives of phi sigma are all 0, and therefore phi sigma is a constant. But you should know the rigorous proof of that. But you'll if you see if you can work it out for yourself, you'll find the argument in the text if you get stuck. But try to work it out for yourself. So this is this implies that phi sigma is constant. Constant. So that means we can pull that out the front. It's constant. And now we just let sigma tend to 0. As sigma tends to 0 on this side, this just, of course, tends to Ta of dx1 up to dxn. Because remember, A sigma converges together with all its derivatives. Remember, we checked that for mollifying, everything converges. All the derivatives converge, the supports remain fixed, and everything converges. So T is a current, and this converges to that in the appropriate sense for current. So this is certainly correct. As sigma tends to 0, that tends to TA. But that means this remains bounded, because you can take A positive everywhere except where it's 0, of course, but A positive in some region. That means this is positive times this thing remains bounded. So phi sigma is bounded. So there's some subsequence, theta sigma j converges to theta, constant. It can't become unbounded. That's the point. So that's it. This is, so T. So therefore, let's finish it here. So this guy, T of A dx1 up to dxn is equal to a constant theta times the integral over A. But this, by definition, this integral here is exactly the definition of U hitting, well, it's rather the, yeah, it's U hitting A because A's got some compact support in U. In fact, it's got compact support in this ball. It's U hitting A dx1 up to dxn. It's just another way of writing the same thing, and I've still got the factor of theta, constant factor of theta. So that's the same thing. So this means this is equal to this. dxn. So that's it. That's the proof. We proved that T is equal to C times U. Now, for later purposes, I want to mention something. I don't think I've got time to give the proof, but let me mention it. If you drop this hypothesis, if you assume MW boundary is merely finite instead of 0, so this is an important extra note. If you just hypothesize that rather than this, how does it change this proof? Well, it changes this proof in that this is no longer 0, but at least it's bounded. Less than a constant times A. Then the same argument gives integral dja times theta sigma dln absolute value is less than or equal to a constant times sup mod A. At least we would get that. Now this says that the distribution derivatives of phi sigma are in L1. That's not really. It doesn't quite say that. It says that the distribution derivatives are measures. So I'm not going to give the details of this proof because we didn't talk about BV functions previously. But if you're interested in following this up, you need to look at the section on BV functions. And the claim is that this hypothesis, let's call this inequality star implies theta sigma is in BV, and even with a norm. See, this is a fixed constant independent of theta. Independent of sigma, sorry. Independent of sigma. So theta is in BV with norm less than or equal to C, independent of sigma. So admittedly, we no longer get the conclusion that we had before. We no longer get a constant. But what we do get is that theta sigma, there's a compactness theorem in BV. which applies whenever you have uniformly bounded like this, that it means that theta sigma j for some sequence tending to 0 converges to theta, which is in L1. In fact, it's in BV. So, so in other words, if you just hypothesize the mass of the boundary should be finite for every W compactly contained in U, then you still get a conclusion. You get that T can be represented in terms of a BV function, namely theta A theta dln, integral over B rho x0. Oh, you can write it integral over U because in any case A's got compact support. So this is for A and C infinity with compact support in the open ball. And that's a very useful fact. We're going to make use of it later. Sorry, I don't have time to give this discussion of BV functions, but I think you can read that up for yourself. It's not very complicated, that section. Okay, so that's the constancy theorem and this extra remark on the constancy theorem. In fact, I'm going to refer to this later today, so let's call this note star. I'm going to refer to this star. Okay, so that's that. Now let's see what else. Oh yes, we still haven't talked. We've still got a bit more machinery. Notice we're slowly getting the machinery of currents together now. Another bit of machinery that we need is the notion of Cartesian product of currents. So suppose we've got T1, which is a current of dimension N1 in U1, or in general, Tj is of dimension Nj in Uj, j equals 1 to 2. So you've got two currents of different dimensions. And then we want to talk about what's the right definition of T1 Cartesian product T2. So we want to work that out. Now remember, when you're trying to work out the right definition for something, it's usually good to go back to the prototypical example again. Remember, the prototypical example was the example of a manifold. So in this case, there would be two manifolds. So we had, suppose that M1 and M2, Mj contained in Uj, this is now a C2 submanifold, or a C1 submanifold, I guess would be enough, of dimension Nj, dimension N sub j, j equals 1 to 2. And we want to talk about what the right definition of M1 cross M2 is, of course, oriented. Remember, if you want to use the prototypical example, you need to be talking about oriented n-dimensional manifolds, because you have to be able to integrate forms over the manifold in order to use it as an example of a current. So what's the right definition of that? Well, obviously, we'd want this to work out. So let's work out these. So M1 would have an orientation Xi1, let's call it. And remember, that would just be T11 up to T1N1. So generally, Mj would have an orientation Xij, which would be an orthonormal basis for the tangent space. And this would be wedge product. Remember, an orientation is a choice of n vectors, in this case a choice of n1 vectors and n2 vectors in the wedging together orthonormal basis for the tangent space. Mj, j equals 1, 2, and this would be plus or minus, but of course we would choose choose it so that it's continuous, right? Orientable means that you can choose, make a choice of plus minus at each point so that it becomes a continuous function. This guy becomes continuous, k vector, and so then what would be the correct orientation for this if we want this to work out? So this is what we'd want, obviously. And well, I haven't said what this means yet, but yeah, we'd want this to be defined. So maybe I should have written this the other way around, I suppose, if we're using it as the definition. So we'd want to define a Cartesian product M1, Cartesian product M2, so that it works out to be exactly just the current corresponding to the Cartesian product. And remember, this guy has orientation. Xi1 wedge Xi2. Now stare at that for a minute and tell me what's wrong with that statement. I claim that doesn't make any sense. Do you see what's a little technicality? It's because when we wedge vectors, they're supposed to be in the same space, right? In our case, they're supposed to be in the same Euclidean space. Now these are not. This one is in the space RP1. And this one's in the Euclidean space RP, or omega N1. And this one's in the form a k vector in the, these are k vectors, so they're subscripts. N1, N2, RP2, P1 and P2. And we normally don't wedge, so you'd say, well, that's just a technicality. Yeah, but it turns out it's an important technicality here, so we'd better get this exactly right. So let P of x equals x0 in RP1 cross 0 contained in RP1 cross P2. And let, this is P1, and let P2, let's call these P and Q. I think that's the way it's done in the text, so let's stick to that notation. And let's call Q of y to be equal to 0y in 0 cross RP2. Sort of seems like we're being a bit picky here, but it turns out to be important. So that means this is not really Xi1 wedge Xi2, it's the push forward of Xi1 wedged with the push forward of Xi2. Then they're in the same space, in the correct part of the same space. This one lives in the subspace 0 cross RP2, and this one lives in the subspace RP1 cross 0. So that's the correct definition of the orientation. Sounds like I'm being really picky there, but believe me, you need to do that. Otherwise you get things that don't really make much sense. And that works out pretty well because in terms of these basis vectors, you see doing this is like taking the basis vectors tor Xi1, taking the basis vectors tor1, 0 up to tor n1, 0 instead of tor1 up to tor n, and wedging those with the other choice, that's the basis vectors, well, right, so these these I2 would be Tor, so this would be Tor 1 up to Tor n0, and the others would be Tor 0, Tor 2, 1 up to 0, Tor 2, n2. Okay, so that's the way we define the, so that's the way we should define the Cartesian product. We want it to work out like this, obviously. If you want it to be correct for manifolds, you definitely want this to be true. So what's the right definition in general then? So let me tell you the answer to that, and then you can check that it's correct. So I've got to say what T1, so here's the definition. I've got to say what this does to an N1 plus N2 form in RP1 cross RP2. So an N1 plus MP2, an N1 plus N2 form has this form. Alpha Ni N1 P1, beta Ni N2 P2, and coefficients depending on the two variables x and y in respectively in RP1 and in RP2. And then you'd have, oh, this is A alpha beta. And then you'd have dx alpha wedge dy beta, like that. And I've got to say what that is. Well, here's the definition. So actually, yeah, so this is T1 applied to the T1 applied to the x part of this form. So A alpha beta A alpha beta xy dx alpha, and then wedge, then dy beta, no wedge, just dy beta, and then I want to apply T2. Now, first thing, so this is supposed to be the definition, but we'd better check that it makes sense. First of all, this bit certainly makes sense, because if you freeze y, this is a C infinity function with compact support. I mean, these coefficients, C infinity with compact support. So that certainly makes sense. But there's one other thing to check here. To make sense, that what I've bracketed here as a function of y should be a C infinity function with compact support, right? Because I want to apply T2 to it. So this is, I claim that this is in C infinity with compact support in U2 as a function of y. And there's a little thing to check there. You've just got to use difference quotients and the linearity of T1 and the fact that T1 is a continuous linear functional to check that that's really correct. There's a few steps to check that, but I claim that that's true. So I'll leave you to check that. So claim is that that's correct. So this does indeed make sense. Oops, I forgot to sum. Sum over beta in I n2 p2 of this. Okay, so that's, I left you something to check there. But it is true. So that's our definition. And the claim is, in fact, it's rather easy to check now once you're convinced that's the correct definition. The claim is that if you take two forms, omega 1 in dn1, let's say it this way. Take two forms, omega 1 in dr of u1, some dimension r, and omega 2 in ds. Oh, yes, sorry. Yeah, actually, I cheated you there. You see what I've done here? that's not the most general form in the product space. The most general form in the product space is alpha in I R P1 and beta in I S P1 with R plus S equals N1 plus N2. That's the most general form, right? Otherwise, I wouldn't be giving the definition completely. But if we go back to this case here, you see that whenever you take a form that's, if you take a form that's the wrong dimension, take something R and S, where R and S merely add the same as N plus T, that should be measured as 0 here. So the definition should be that this Cartesian product ignores all the terms other than where alpha is equal to N1 in IN1 P1 and beta is in IN2 P2. It just ignores all the other terms, just drops them. So that is, in other words, you can check this, that if this is indeed, if you take two such forms, remember U1 is contained in RP1 and U2 is contained in RP2, then using our definition there, you see that T1 cross T2 of omega wedge omega 2, and again, we've got to be a bit careful here. These are in different spaces. So I want to pull them back. Remember, you pull back forms, not push them. So I want to pull them back. So I'm going to use a pull back P for omega 1. So P is going to be the projection that takes a point xy and gives you x. And Q, similarly, is going to be a projection that takes xy and gives you y. And then I'm going to do omega 1 wedge Q sharp omega 2. And now this does make sense because both of these are living in the Cartesian product space, right? In the space RP1 cross RP2. They're both smooth forms in RP1 cross RP2. Without the pullbacks, it wouldn't make sense for the similar reason that the Xi1 wedge Xi2 didn't make sense there. Okay, so I claim that using this definition is equivalent to saying that this is equal to 0 if Rs is not equal to N1, N2. And it's equal to T1 omega 1 times T2 omega 2 if Rs equals N1, N2. So it's a bit complicated, but that's the way it works out, right? So you've got to get used to that. That's the way Cartesian product of forms go. And notice that if we do make that definition, this certainly works out. So the prototype works out, and this seems to be the correct definition. Okay, so now let's list some facts, which I'll leave you, in general, leave you to check. They're very easy to check, these facts. Several facts that we're going to need using this definition. First fact is that the first fact is that M W1 cross W2 of T1 cross T2 is just the product of the masses. All of these are easily checked, so I'll just leave it for you to check. So that's the first fact. Second fact is that if this is finite, for every W properly contained in U1 cross U2, then remember that means that you can represent the current by integration. So you get a measure, a for L regular locally finite measure and an arrow direction for t. So the claim is that then T1 cross T2 arrow is the same as T1 arrow wedged with T2 arrow, except that again, that doesn't quite make sense. You've got to do the same P star Q star thing that we used over there. Same procedure that we used for the prototypical example over there. And furthermore, the measure is the same as the product measure. That's very nice. The product, it works out to be a product measure. Well, I think you can see that happening here, right? That's going to, in case these are given by integration, that's clearly going to mean Fubini's theorem holds, right? So it's going to work out as a product measure. So that's the second property. And then, oh yes, there's a couple of other ones here. 3, boundary of T1 cross T2 is just boundary of T1 cross T2 plus, now you've got to be careful of a sign here, it's minus 1 to the N1 T1 cross boundary of T2, like that. And yeah, I think that's enough of those for the moment. Oh, and then there's some special cases. So there's general formulae, so I'll leave you to check those. And then there's some special cases. When T1 is just the one-dimensional current on R given by integration over the unit interval. Remember, that just means that T1 of A dx1 is just equal to the integral from 0 to 1 of A T dt. Or AX1 dx1, if you like, call it whatever you like. So if T1 is that and T2 is some other T in dNu, then you can take the special case then of the Cartesian product of those. And first thing is, for this one, you can check. And again, this is pretty easy to check, just following the definitions. The arrow vector for that one-dimensional current, of course, is just the number 1, scalar, number 1. And the measure for that one-dimensional current in R1 is just Lebesgue one-dimensional measure restricted to the interval 0, 1, like so. And if you take 0, 1 Cartesian product with T, it's this guy, that's and you take the arrow of that, that's just 1 times T arrow, so it's just T arrow, like that. And oh yeah, I got that wrong, didn't I? This is, no, see, that's what you'd get if you don't respect your P's and Q's. P sharp of 1 is E1. Not 1, not the number 1, it's E1. It's the vector whose first component is 1 and the remaining component is 0. So that's what you get if you're not careful. So this is E1 wedge T arrow. Yep, have to keep your wits about you. Oh, and I still made a mistake. This is Q star T arrow. Otherwise you run into the similar problem with T. And then boundary of this current, one-dimensional current, hitting a form. Well, let's work it out. I've got to hit a form. So a form is just a times dx1 in that case. Well, that's just the, by definition, that's just the current 0, 1 hitting the exterior derivative of this. So this is d, oh, sorry, stupid. That's not a 1 current, this is a 0 current, right? It's the boundary of a 1 current, that's a 0 current. That means you've got to hit a function. So f is in C infinity with compact support on the unit interval, 0, 1. So we've got to say what that is. Well, by definition of boundary, that's df, 0, 1 df, which is integral. Remember, this is just the integral. So this is f prime x1 dx1, function on the real line. So this is just integral of f prime t dt from 0 to 1, which is f1 minus f0. So easy, it's hard. And so that means, what does that say in terms of current notation? That means that boundary, we've shown that boundary of 0, 1, boundary of that current is, this has just picked out the value at the endpoints of f. So that's f, oh, sorry, this is supposed to be C infinity on R. These are f, this 0, 1 is a current on all of R. So it's a one-dimensional current on all of R. So it just picks out the values at the endpoints, but that's the Dirac delta. The Dirac delta function of at 1 of f minus the Dirac delta function of 0 of f. So this is delta 1 minus delta 0, where delta p is the 0 current. Delta p of f is just equal to fp. Notice that delta p is indeed a current, a 0 current on R. It satisfies the definition of 0 currents on R. Certainly got compact support. It's a continuous on the space D, on the C infinity functions with compact support. So let's see, I think that's about all we need for those guys. Okay. And now, so there's a lot to keep track of here. You see, you shouldn't treat this with too much contempt, because we're putting together a lot of definitions. But you'll see by the time we've put together all the definitions, you get an extremely powerful machine. Even though each little bit didn't seem to be anything much at all, when you put it all together, you get a very powerful machine, as you'll see as we go along. So let's prove something now. A bit more interesting. I want to prove the homotopy formula. So the homotopy formula, this is rather important. So you take a current T in D and U. U is open in RP. And you take a function h of n, you take a function h which is defined on the closed unit interval cross u into u. and you take two functions fg in C infinity with compact support in U. Oh, no. No, that's not right. You take two functions fg which are maps. Which are maps U into U, and then you define a function h on the Cartesian product of the closed unit interval cross U back to U, and you define it with the property rather. This should be C infinity, and it should have the property that h of 1x is identically equal to gx, and h of 0x is identically equal to f of x. So you see, that's why the word homotopy. So h provides a homotopy starting with f and ending with g, right? Homotopy. And furthermore, h should be proper. H restricted to the support of to 0, 1 cross the support of t should be proper. Should be proper. Then the boundary of h sharp 0, 1 cross t is equal to g sharp t minus f sharp t plus, or minus rather, 0, 1 h sharp 0, 1 cross boundary of t. And in particular, boundary t equals 0 implies that boundary of h sharp 0, 1 cross t is equal to g sharp t minus f sharp t. So that's the way to look at this. The homotopy formula gives you a way of cooking up a new current of one higher dimension than you started with in such a way that the boundary of this new current is equal to the difference of the two currents that you get by pushing forward with G and F respectively. That's the way to look at it. You should think of this as just sort of being an extra term that you can't get rid of unless the boundary of T is 0. The important part, at least from understanding what the formula is saying, is these three terms. So I'll show you, we'll check that. Let's take a break for 10 minutes and we'll check this to make sure this is correct. Yeah.
So I wanted to ask you a couple of things about your talk before.
Yes.
I mean, this is all funny. I was just thinking you remind me with Singe's theorem and stuff like that.
Yes, yeah, it's great, isn't it? I love that theorem.
So the argument, you always got to get the embedded geodesic. So,
yeah. Yeah.
So
actually, I don't think it matters whether I think for that argument, I don't think it matters whether yeah, well, maybe it does, because you're taking the second variation. Yeah, you're right. It does matter. It does matter, that's right. So you've got to take a free homotopy. Yeah.
Right, that's
funny. Yeah.
No, I mean, you know.
Yeah, no, I swept that under the carpet.
No, it's okay. That's fine. And the same thing you have to worry about, when you do the higher dimensional.
But you see, if it crosses itself, and then you can just pinch it off and use one of those halves, you see. Yeah. You're right, though. You definitely need embedded because you're using the ambient stuff, right? Yep. Yep.
Yeah. And this is very stupid. The density could be 2 minus alpha or something like that, Instead of density 1, you're when you say,
Oh, yes, that's right. That's right.
As long as you can keep away from.
Yeah, that's right. In fact, I love that theorem. As soon as you've got density less than 2, all those branch things go away.
Yeah. Oh, yeah.
But I hadn't quite realized before that as far as the plateau problems is concerned, you can just forget multiplicity once you've got Freddy's regularity. That all goes away. Theta is identically 1 on the regular set then.
Well, yeah, I mean, sort of locally, right?
I think it's probably, isn't it, sort of globally, though, if you take an embedded boundary.
Put them in the same place.
No, I mean, you've got to take a connected embedded boundary.
Connected regular boundary.
Oh, fuck off.
People start doing these things.
Yeah, I know.
With funny multiplicities.
I know, there are, of course, examples like that, but in general, I think that's right.
No, but the point is once you have the regularity, in fact, even n-1 measures 0 or something.
Yeah, that's right. Exactly. n-1 measures 0.
Right,
yeah.
Then you can zoom around.
Yeah, you can zoom around.
Your multiplicity spreads out.
Unless you hit the boundary, nothing can change.
Yeah.
Yeah, that's right.
And so if you got the multiplicity constant at the boundary, then it spreads.
Yeah.
It's sort of just false branch points. That was the big deal with
the Germans.
Oh, yeah.
The Germans could be dense. They're very smart people, but they could be dense about something. The Germans used to agonize about this false branch. I mean, it's trivial.
Z to Z squared, for example.
Yeah, they used to really agonize over this. I think it's because they looked at everything analytically, not geometrically.
That's why they got used to Osterman's observation.
Yeah, they wouldn't accept, Jaeger in particular. I think to his dying day, he's not dead yet actually, to his dying day will keep saying Osterman was completely wrong. Even though it was just a minor glitch in the proof that was easily fixed up, he'll say it was completely wrong. I think Jaeger is a bit of a bastard, actually. I don't think you'd want to cross him, actually.
No.
He's really weird because he's got tremendous influence in the German system. And it's sort of exceptional because he really didn't do much. Normally in the German system, you have to have done something really big, right? But he's sort of the exception to that. Maybe that makes him even more dangerous and vicious. Because he's a little bit insecure, perhaps.
Well, I hate to bring up an unpleasant topic, but you think about this president. I mean, what the shit did he do? And here he is fighting Comey. Comey was the head of the damn FBI. The head of the FBI. He had all this experience.
It goes on and on, though, Paul.
Everybody.
It goes on and on. He's destroying the diplomatic relations of America with everybody.
Everything.
He's making the whole country a laughing. By the way, I'm a citizen these days, so this hurts me a bit too.
Your mistake.
Yeah.
You blew it.
I blew it. It is extremely worrying. And see, what I wouldn't care except that you see this phenomenon played out every week, that you think the next thing he does must cause his popularity to plummet. No such thing.
He does something more outrageous.
Right, and it doesn't plummet. He's got his same core support. It's growing even.
Well, I don't know. I mean, they kept talking about, oh, his popularity shrinking. But then
It's not.
it starts going back.
It hit a wall. He's around 35%, and that's enough of a base to launch anything that he wants. I really think I think it's a bit sinister, actually.
Our good friend Adolf, where was he at? He wasn't.
No, he was the adoring public until he started losing.
Yeah.
Have you ever seen any of these pictures that Lenny, movies taken from the car, showing the crowds as he's...
Unbelievable.
The adoration is unbelievable. Every man, woman, and child, particularly the women I noticed, adoring.
Oh, yeah.
And of course, after the war, oh no, I wasn't a Nazi.
Well, we're going to have to...
Can I ask a question?
Yes.
Why should we introduce the wedge operator on vectors? Because usually we use wedge products on forms.
Yeah, on forms. It's because of the duality. It's better to orient the currents by k vectors. Because of the way you push forward, it's more logical to use forms for the it's more logical to use n vectors rather than n forms. Yeah.
So,
But it's sort of a notational thing more than anything. It's isomorphic, I mean,
yes.
right? It's isometrically isomorphic.
So I think that's a strange location. You talked about P push forward.
Yes.
T
Yes.
example, but
Yeah.
I thought push forward is only defined on the image.
No, I only push forward the k vectors. You push forward vectors and you pull back forms. I only use so see here, this guy, see what, this is this is an n vector. So this makes sense. But then this guy, again, n vector, right? And I've erased the other one, I think, unless it's still here. Here it is. See, here you're pulling back, so you've got to use these guys. And notice this P is not the same. This is an uppercase P. It's the projection. Whereas the little...
If you really want to get confused, you write this. They're adjoint maps.
Yeah, they're adjoints, right. Yeah, they're adjoints. That emphasizes the duality then.
But
Yeah,
I mean, so
yeah,
push forward is like this.
that's right, with little p.
Yeah. So say you
A
have
vector, that's a k vector.
yeah,
Yeah.
that's P of X.
Well, there's no need to even think of it as a variable. You can just do it at the linear algebra level. Think of this as a constant k vector. Or maybe you don't want to do that. Maybe you want to work out what this is saying. Here it is. So this gives you something that if you take this at x, this gives you something at x0. And likewise, this guy lives at the point 0y.
Yeah, that's my point. That
Yeah.
that is not defined on anywhere where y is not equal to 0.
What's that?
So so this one is defined on x0.
Yes.
And this one is defined
Yes.
on
But this guy is defined at x.
yeah.
Before you push it, it's defined at x.
Yeah.
Then you push it, you get something defined at x0. It's only a small difference between the things, of course. Sometimes you sometimes you sweep that under the rug, right, that difference between x. Sometimes you identify r cross 0 with r, right? But in this case, that would not be a good idea because it wouldn't really make sense. But anyway, let me know if that doesn't make sense to you. I think you'll find it all hangs together.
Well, I definitely know what you're trying to talk about.
Yeah, yeah,
I think
yeah.
that would maybe pullback would be more exactly what you're saying.
Yeah.
It's not always worth finding.
Yeah, but I think you really do have to do that. Otherwise, you run into you saw it here actually, right? if I hadn't have remembered that this was P sharp, push of the number 1, that's the vector E1. See, that makes a difference. It really does. Yeah. Yeah. Yep. Okay. Okay, let's start again. Okay, so we need to prove this. And I think you can see the proof's pretty clear, because remember, push forward. Yeah. Oh, okay, we lost our pattern. The light's still on. Oh, on that one. Okay. Maybe it's just turned off. Okay, we'll fish that out. Maybe it's... Okay, great.
Okay,
Thanks. Yeah, as I said, I think you can see how this is going to work, because remember, boundary commutes with pushing forward, so that's the first step. So boundary H sharp 0, 1 cross T is H sharp of the boundary 0, 1 cross T. And then the boundary, it's one of our identities here, I think. Here it is. Well, it's the boundary of this bit we know is the difference of the Dirac delta functions, and the boundary of the Cartesian product follows this formula. We've got to remember, in this case, our T1 is just the one form, the one current living on 0, 1. So this, in this case, N1 would be 1, so there'll be a minus sign here. So this is H sharp. Now we take first the boundary of this, which is the Dirac delta at 1 minus the Dirac delta at 0, Cartesian product with T. And then we've got to do the boundary of this, but there's a minus sign because we're crossing a one current. So this is a minus H sharp 0, 1 cross boundary of T. Well, this bit's good because it's this, so we've got that bit. And clearly, delta 1 cross T, H sharp delta 1 cross T, well, you've just got to check. So this is the same as H sharp delta 1 cross T minus H sharp delta 0 cross T minus this, which is what we wanted. And now you've just got to check, following the definitions, that this is the same as, remember, H at 1 is equal to G, right? So you've just got to check, this is just G sharp of T minus F sharp of T. And then we've got this term minus that. So that's it. So that works out. Okay, so that's the homotopy formula. Now there's a couple of important applications of the homotopy formula, and one in particular that I want to do here. Yep. Yep. Right. Do this. I think we can get rid of this now. So, lemma. So this is the first application of the homotopy formula. lemma. So suppose that you've got a current, an N current, and suppose that mass of the current and its boundary are both finite locally. Finite for every W properly contained in U. And suppose that you've got two maps, F and G. Oh, yeah, sorry. I've just realized I've got to, before I state that theorem, I've got to do something else here. So I'm going to talk about, we're going to need, in this, what I'm about to show here, I'm going to need, oh, actually, maybe it doesn't matter. No, actually, it's okay. No, it's not okay, right? Okay. So, so let's see. Let's look at a special case of this homotopy. An important special case. So H is a general homotopy. I'm going to look at an affine homotopy. So this is one where ht of x is equal to t of gx plus 1 minus t fx. Notice that's a special case of this, because when you take t equals 1, you get g, and when you take t equals 0, you get f, right? So it's a special case. But we'd better make sure, so notice we'd better be in a star-shaped domain from the origin, otherwise this will take us outside the domain. So use star-shaped from 0. So 0 is somewhere inside the domain, and the domain's got the property that if you have a point y in the domain, then the whole ray joining y to the origin is also in the domain, right? Star-shaped. Oh, sorry, right, yeah. Right, I'm getting confused. What am I getting confused with? We need a star shape for something. Oh, yes, that's when we talk about a cone, that's right. So this is convex, U convex. Because we do want to take the convex. So F and G are U into U. U convex is C infinity. U convex. And this for t, so that's for t between 0 and 1. X in U. Yeah, thanks, Bob. Somehow getting confused. The star-shaped thing will come up in a minute when we talk about cones. The cone over a current. So X in U, and of course we need H proper. Notice that's definitely not guaranteed by F and G being proper. That's a common misconception. Because you could take F, you could take U symmetric and take F equals minus G. And then when you get to the halfway along this homotopy, it's a constant map, which is not proper. Right? So you've got to hypothesize H is still proper, part of the hypotheses. Then you have this formula, and I wanted to point something out, though, about this formula. So let's look at H sharp of 0, 1 cross T in this case. And let's also assume that we're working with a current which is finite mass, locally. And let's work this out now. All right, well, this is supposed to be hitting a form, so yeah, this is an n plus 1 form, hitting an n plus 1 form, so that would be omega 1 alpha, depending on two variables, t and x, dt dx alpha. So it would look like that. So what is that? So that's, okay, so yeah, I've erased, I shouldn't have, I was a bit premature in erasing that. Remember, we've got the arrow for 0, 1 cross t is the same as E1 wedge Q sharp T arrow. So that can be written as integral. Remember, we can, with this finiteness of mass, we can write this as an integral. Let's see, do I have this down here? Right. Okay, so, right. Everything's falling apart now. Okay, so this then becomes, okay, so so this is omega. Now, according to our general formula pushing forward, this would be the 0, 1 cross t, pull back h sharp of omega, and that would be the integral of h sharp omega dual pairing with the t arrow of this. Now the t arrow of this, remember, is E1, as I've written over there. The E1 wedge Q sharp t arrow, and it's d mu t. And h sharp by definition means d xt, it's variables tx, dh at tx sharp pullback of omega at the image point. Takes a bit of getting used to this formalism. Dual pairing with E1 wedge Q sharp T. Dual pairing. That's what that looks like. And then we can push this by duality onto here. So that's equal to take that and push this forward. Now when you push this forward, the derivative with respect to t gives you just the partial derivative. This E1 gives you the partial derivative of h with respect to t, the t variable. That's, notice this is f of x plus t times g x minus fx at affine homotopy. So you'll get omega at the image point, htx, dual paired with the partial with respect to t. Now the partial with respect to t is just g minus f. And then we're wedging that with the push forward of this bit, which is exactly just, oh, sorry, I've left off the arrow, which is exactly dx, dh, t, h at tx, but the x part, not sure what the right notation for that is, push forward of t arrow. and then d mu t, and then dt. Remember I think we may still have it here, do we? No. Remember oh, maybe we do. Yeah, here it is. The measure of the Cartesian product is just the product measure. In this case, the first one is Lebesgue measure on the real line, the 0, 1 part. So this gives us the Lebesgue measure from 0 to 1. And this bit is integral over u, d mu t. Okay, that's good. So that means that now so that the upshot is, you see, that the mass in W, in 0, 1 cross W of this push forward current is less than or equal to, well, this bit's less than or equal to sup of G minus F. Sup over the support, over U, if you like. Remember, these have got, they're living in U, so it's sup over, oh, in fact, we're working in W, aren't we? So this is integral over W. So sup over W, G minus F. And then we get this bit. Now, we've got to be careful about this. This is the x derivatives, so it's t times dgx plus 1 minus t times dfx. So I should have written it that way, preferably. T times dx, dgx plus 1 minus t dfx sharp t arrow. Now we've got to be careful about this guy, because remember this is an n vector. So you get actually the nth power. The sup of this to the nth power is the upper bound for this, not the first power. The G minus F is the first power, but you get the nth power of this. So you get sup T dgx plus 1 minus T dfx. This is the norm of the linear map to the nth power. Nth power times the length of t, which is a unit vector, so that doesn't give us anything. And there's a constant c that comes here. You've got to be a bit careful about this. See, t is not necessarily a simple vector, so t has got the general form v alpha e alpha, where it's a unit vector, so the sum of v alpha squared equals 1, right? That's what it looks like. So if you take a linear map, L sharp t, I mean, that's what we're doing here, right? This is a linear map applied to t arrow. Well, that's the sum of v alpha, L sharp e alpha. And that's less than or equal to the square root of the sum of squares of the v alpha squared times the square root of the nth power of the norm squared. Times 1. And this is, yeah. And this is summed, see, we also have to sum over alpha here. So how many terms are there? Well, this is a small point, but it's important. There are actually p choose n terms in that sum. So you get p choose n as a factor in here. If you use Cauchy-Schwarz inequality, this bit's 1. So this constant that you get here is p choose n. You can take c equals 1 if you know that t arrow is a simple vector. if T arrow can be written in the form V1 up to Vn, then there's just one term then. You don't have to go through this procedure. But in general, you'll get a factor Pn to the 1/2 power. So you do get a constant there. Anyway, this is what you get for the bound on the mass, right? The constant doesn't matter usually, but anyway, we're going to make use of that inequality on the mass for an affine homotopy. So now let's come back to this lemma. Yes, so this f and g, u into u, c infinity, and u convex, because we want to use that affine homotopy, u convex, and f equals g, fx equals gx, for every x in the support of t. Then the claim is that g sharp of t is equal to f sharp of t. Now, you might have believed that without any other hypotheses, because I said f equals g on the support of t. But think about that. It's a bit of a surprise that g sharp t equals f sharp t, because this only says, think of t as being something like our prototypical example, right? Like a manifold. So the support of t would be a manifold. And then saying f equals g on the support of t only says that f equals g on this manifold. But the derivatives of f and g could diverge as you move normal to the manifold. And clearly these operations of pushing forward do depend on derivatives of f and g. So there is something to check here. In a way, this is a bit surprising at first sight. So let's check that it does indeed work out. So proof. Right, we use the homotopy formula. So, right, so the homotopy formula, let's call it star. Yep, right. I don't remember how this goes. Yep. So by star, G sharp T minus F sharp T is equal to boundary of H sharp 0, 1 cross T minus H sharp of 0, 1 cross boundary of T. The plus, because I put that onto the other side, so it becomes plus. So that's a plus sign. So we have that. And now we can write. Now this is right. Okay. Yes. So this is the same as H sharp. I think I'm doing this right. Boundary of this. Remember H sharp and delta commute. Plus this term. And now we use this mass. The mass of the H sharp pushing any current forward, as long as it's got finite mass, is less than or equal to sup over W. Now I should have said, sorry, this is W intersect the support of T. Because you see, this is only involves the support of T, because this is d mu T, integrating with respect to the measure mu T. So you get 0 for almost all points which are not in the support. So this is W intersect support of T, which is 0 in our case, because F and G are 0. So mass of both of these is 0. So mass W of G sharp t minus f sharp t is equal to 0, because both of these terms are 0. And for this term, you use what's on the right board with boundary t in place of t. And for this one, yeah, somehow I've got something wrong here. Let's see. Right, what did I do wrong there? How do we handle this term? Seem to have something not quite right there. Hold on. Oh, right, yeah. Yeah, so I think, yeah, that's right. This is wrong. Don't do that. Just plug in a form. And this is plug in a form omega, and then by definition of D, that's this current hitting D omega. Hitting D omega, and this current hitting omega. Hitting omega. That's correct. Now, that means that mod of the difference is less than or equal to the mass of that, which is 0 times the sup of d omega. Less than or equal to 0 times the sup by that inequality on the right board over there. Sup mod d omega. Plus, again, 0. Using the right board with boundary of t in place of t. Again, 0 times sup omega. By definition of mass, which is 0. So that's it. Yeah. Probably. Let's see. Yeah, in the inequality. Yes, I did. Mass, thanks. Mass W of T. Yeah, thanks. Okay, so that worked out. All right, so it's a bit tedious, I know. There's so much machinery to set up, but believe me, this turns out to be an extremely powerful machine in the end. In fact, let me state this theorem. I'm probably not going to have quite time to prove it today, so I'll defer it until next time, but let me state the result. So, I think we can get rid of this now. Okay, so here's a theorem that's going to be rather important in proving the compactness theorem. So take E contained in U with n-dimensional measure of E equal to 0. And take a current, an N current, with locally finite mass and also the boundary locally finite mass. Less than infinity. And then, this is for every W properly contained in U as usual. Then, mu T, yeah, oh, sorry. It's better to not state it like that. Just simply take a current. So take a current with locally finite mass and the boundary locally finite mass for every W properly contained in U. Then the measure mu t. Remember, T having locally finite mass means there's a corresponding measure, right? That's part of our general knowledge. Then mu t is absolutely continuous with respect to Hausdorff n-dimensional measure. In other words, HNE equals 0 implies mu t E equals 0. Very nice fact. And now you've got to think about your course in measure theory. Remember what one measure being absolutely continuous with respect to another guarantees? By the Radon-Nikodym theorem, that means that actually this measure is just a function times this measure. So by Radon-Nikodym, there exists a positive function theta, a non-negative rather, non-negative Borel measurable, and in particular mu t measurable in that case, Borel measurable function theta such that d mu equals theta times dHn. In other words, integral the measure of a set A, any Borel set A is just the integral over A of theta dHn. Measure mu t. So that's actually rather good. It's I know it's hard to keep track of all these tiny little facts, but MW being finite, remember, already means there's a measure. So it starts to look like the prototypical example of a manifold, but not really, because it's just an abstract measure. But now, if you also assume the boundary has finite mass, then you do indeed get theta dHn. So that means that T omega, when you represent it by integration, instead of just getting an abstract measure mu t here, it looks like the prototypical example. You get theta dHn, just like the prototypical example. What you don't have yet is a rectifiable set, though. That requires more than just, this is still more general, but it starts to look more like the prototypical example of a manifold. So this is omega dual pairing with T. Like that. So that actually, this is a nice theorem. And the proof of this is a bit lengthy, so I think I'd better defer it until next time. Right, so that's, and you'll see that actually that's, the proof of this doesn't require that much effort, even though it's a rather deep result, I think, at least. It doesn't require much effort because we have so much machinery at our disposal now. Okay, so let me finish today by introducing integer multiplicity currents. So take M to be an n-rectifiable set. And theta positive integer valued, integer valued Hn measurable function. So a positive Hn measurable with with theta x in the positive integers, hn almost everywhere. Almost every x in m. And finally, let xi be equal to plus or minus tau 1 wedge xi at x, plus or minus tau 1 wedge up to tau n, where this is an orthonormal basis for the approximate tangent space. And let's suppose that this is at least Borel measurable. It needn't be continuous. In fact, it doesn't make much sense to say it's continuous because M is only a rectifiable set. It's not a smooth manifold, so it doesn't really make much sense to require it to be continuous. But psi is at least Borel measurable. Or Hn measurable is fine. In particular, it could be Borel measurable, but as long as it's Hn measurable, that's fine. Immeasurable. Then you define a current, T omega, just as you would if M were a smooth manifold. You simply define this to be the integral over M of the dual pairing omega with this n vector. This is an n vector. Notice this psi at x is in the set of n vectors in Rp. This is all happening in some open set in Rp. So this is in Rp for Hn almost every x in omega, in M. And that's the dual pairing. And then it's theta dhn. So you get this. So this looks exactly like the prototypical example, including the orientation, except that, of course, it no longer makes any sense to require xi to be a continuous orientation. Just measurable is all you can expect, unless you know something about the smoothness of M. And we've got this multiplicity function, which is integer valued almost everywhere. Anyway, this is certainly, notice that T is definitely a current, no question, and it's a current with finite mass. In fact, the mass, locally finite mass, the mass of W, oh, should have said that, N rectifiable in U and Hn M intersect W, K, finite. For every K, for every compact K contained in U. And MW, notice, is the mass. Well, it's the usual thing. I think you can see if you take the soup over all smooth n forms with length less than or equal to 1, you'll clearly get, you can make that as close to 1 as you like, except on a set of small measure. And then by passing to the limit, you actually simply get 1 times the integral of theta over the set M intersect W. So this becomes M intersect W theta dhn. And that's less than infinity if theta is locally integrable. In U. So, so certainly it's a current, and you know, I guess, right. Actually, I don't think I said this quite right for the following reason. We definitely need this to be finite in order for this integral to be well defined, right? It's a signed integral. This is a Lebesgue integration. It's a signed, this function takes a sign, so in order for it to be even well defined, you need this. So instead of saying this, I actually more correctly should have said integral theta m intersect k dhn less than infinity for every compact k. Contained in U. That's the correct formulation. Then indeed this is a current. Then it's clearly continuous linear functional on the smooth n forms with compact support as long as you have this finiteness property. Okay, so that's the definition, and any such current you call an integer multiplicity rectifiable current. It lives on a rectifiable set, it's got an orientation, and it's got a multiplicity function. So we use the notation so the notation is T equals tau underline m theta xi. Whenever we write this, we mean this, right? And we refer to these things as integer multiplicity rectifiable currents, or just integer multiplicity currents. Important class of currents, because this really is the natural generalization of the prototypical example, except instead of a smooth manifold, you've now got a rectifiable set. And notice it also ties in with our previous discussion of rectifiable varifolds, because if you simply drop the orientation, then you've got this pair. M theta was exactly what an integer multiplicity varifold. So this is a rectifiable varifold in the sense that we defined it before. And this is, it's called the corresponding rectifiable varifold. So in other words, you start with a current, including an orientation, and you drop the orientation, then you're left with a varifold. And notice the mass of the varifold is exactly the same as the mass of the current. Both are equal. So mass of the varifold in W is exactly the same. It's the integral over m intersect W of theta dhn. It's exactly the same. All right, so that's the notion of integer multiplicity varifold. And we'll talk a little bit more about them next time. I want to talk about pushing forward and so forth. But that works out very similar to the smooth case. And I just want to end today by stating the Federer-Fleming compactness theorem. So suppose TQ is any sequence of integer multiplicity rectifiable currents with mass in W of TQ and sup over all Q, mass in W of TQ plus the mass of the boundaries. So you need to assume both the mass of the currents and the mass of their boundaries are locally finite. Then there exists a subsequence TQ prime and an integer multiplicity current T with TQ prime omega converges to T omega for every form with compact support. As I mentioned a week or two ago, an amazing theorem. You know, at first sight, I wouldn't have believed it was possible that could be true. It's only true because of you get cancellations. If things become too pathological, things tend to cancel out. And you still get left with, I mean, as I pointed out a few sessions ago, that nothing like this is true if you take varifolds, because then you can take, you know, we had an example of a whole lot of vertical cylinders which have finite mass, locally finite mass, but then when you pass to the limit, they sort of get smeared out, and you don't get a rectifiable set. You get instead Lebesgue measure in the surrounding space. So it's nothing like this. Okay, so that's it for today. We'll continue our discussion of integer multiplicity currents next time.